Hey AP, in this video we are going to learn about types of acids and bases and pH calculations. So acids are defined in terms of their proton transfer, and a proton is just a hydrogen ion. They're defined in terms of their strength of ionization, so how much can they ionize versus not ionize. And then we also can sort them into acid-base pairs. So then there's two other types of definitions for acids and bases. We have our Bronsted-Lorie acids and bases, which is where we define an acid as a proton donor. So if we say that all acids start with hydrogen, like HNO3, we would say that this is NO, HNO3. So this is nitric acid. So this hydrogen would get donated to something else. It would pop off and be a hydrogen ion. And that therefore is an acidic hydrogen ion, and that is our proton donor. And then a base would come along and be a proton acceptor. So different things can act as bases. Something would accept this hydrogen ion, and that we would consider to be a base. And we'll see that down here. An Arrhenius acid and base looks at what things dissolve into. So an acid would be classified as something that dissolves in water and then produces hydronium ions, which is H3O+. So that we would see here. Some people also ignore the water and just write H+ and just say that it turns into hydrogen ions. And either way, that's fine. For a base would be a substance that dissolves in water and then produces hydroxide ions. And we usually define bases as anything that ends in hydroxide, except for our one exception to this is NH3. NH3 does not end in hydroxide. However, it does act like a base because in water it creates hydroxide ions. So let's take a look at two examples here. So my first example, I have nitric acid, HNO3. So in HNO3, we've got this hydrogen here. Okay, and that's our acidic hydrogen on our acid. Then we can see that we are putting it into water, and this hydrogen on our nitrate here moves. And we can see that our hydrogen moves from being with our nitrate to now not being with our nitrate and then with our water. So our hydrogen goes to the water here. So that makes our nitric acid our acid, and our water here is a base because our water has accepted our hydrogen ion. In our other example, we have NH3 and H2O, and we can see that NH3 goes from 3 hydrogens to 4 hydrogens, and water goes from 2 hydrogens to just 1. So that means one of these hydrogens was donated to our NH3. So that makes water, in this case, a proton donor acid, and then NH3, because it accepted our proton, became a base. Now, on the right-hand side of our reactions, we have made an acid and we've made a base, and we call those conjugates. So you might talk about conjugates in Spanish class or French class, and talk about how you make something into something else. So conjugate pairs is the conjugate is the made or product acid or base. So if we look in our first example, the substance that now holds on to the acidic hydrogen, right, that has accepted it, we've gone from H2 to H3. So this is our conjugate acid because now we've turned it into an acid. And our NO3 has lost the hydrogen, so this becomes our conjugate base because now we've turned it into something that's going to act like a base. So in the second example, here our NH3 has accepted the acidic hydrogen. So now this acidic hydrogen is lying here. So this becomes our conjugate acid because we've made it into an acid. And then this guy's lost our acidic hydrogen, so this one becomes our conjugate base. We can write conjugate base and acid pairs. So the base with the conjugate acid, for our first example up here, our base is H2O, and its conjugate acid is H3O+. And our acid and conjugate base pair, so our acid with the conjugate base, is our HNO3, so our acid, and our conjugate base, NO3-. Okay. We can also talk about the strength of acids and bases. So a strong acid or base will undergo complete ionization, which means it completely dissolves in the solution. which means it's really not in equilibrium at all because it fully goes to the product side or the right side of a reaction. And we see that by having these singular arrows going to the right on these. Okay. Oops. So if we have an acid and our acid is put into water, our acid is going to fully dissolve and we're going to lose that acidic hydrogen. It's going to go to the water. So I'm going to have my acid anion, and then I'm going to have my hydronium ion, my H3O plus. Okay, so this is just a generic acid with a hydrogen on the front. With water, I have this generic anion hanging out. It gets a negative charge, and then my hydronium. In my base of a strong base, now we know that our water is going to act like the acid, which donates to the base here because the base is a proton acceptor. So we're going to get HB as my base. And this usually gets written as HB plus or BH plus. And then I'm going to have hydroxide as my other. And so we can see that from our two definitions up here, we are looking at where the hydrogens are going, and we are making hydronium and hydroxide ions in our solutions here and here. We can also talk about the fact that water can act as both an acid and a base, and then we have a special name for that, and we say that water is amphoteric because it can act like both an acid and a base. Now, when we have weak acids and bases, they have very little ionization, which means that our equilibria really lies to the left side. They don't like to dissolve, and so we treat them a lot like insoluble salts, and so we'll be making ice charts with them, among other things. So they still follow the same format of their products. It's just that now we have these equilibriums established, so we have our double arrow. So same as before, in an example of our acid, the water is still going to donate, the acid is still going to donate the hydrogen to the water. So I'm still going to get A minus and H3O plus. However, it's going to just hang out more so on the left-hand side of my reaction. And then same thing with my base in water. My water is going to donate my hydrogen to my base, so BH plus, and then I'm going to have my hydroxide ions in my solution. So that still happens. It's just the fact that this is going to be at an equilibrium and it's going to hang out more so on the left-hand side of my reaction. We can measure how acidic or basic a solution is by looking at the pH, pOH, hydrogen ion concentration, hydroxide ion concentration of my solution. And you should all be familiar with the pH scale. It tells the relative acidity and basicity of an aqueous solution. So looking at my pH scale, if I have a pH of 7, we know that that is neutral. If I have a pH that is less than 7, all the way up to 6.9999999, that is considered acidic. And if I have a pH above 7, I'm going to have something that is a basic solution. Now I can look at my hydrogen ion concentration based off of my pH. So at a pH of 3, my hydrogen ion concentration is 1 times 10 to negative 3. And this is concentration to a molar. At neutral, 1 times 10 to negative 7 molar. And so when these are whole numbers, these just have a base of 1, so 1 times 10 to the. And we can see that we are going up by a factor of 10 each time. So if a pH of 4 is to be 1 times 10 to the negative 4, pH of 5, 1 times 10 to the negative 5, and so on. So they're increasing by a factor of 10 each time. So if I would go up to from 3, pH of 3 to 5, that's a 100-fold difference in my concentration of hydrogen ions. So continuing, 1 times 10 to negative 11, 1 times 10 to the negative 14. Now my pOH is looking at the potential of hydroxide in here. And what we know about pOH is that pH plus pOH equals 14. So my scale is actually reversed, still 7 here, then 0 here. So I have 3 and 11. So my scale is flipped completely around, which makes sense because I'm measuring the opposite of what's in my solution. And so here at a pOH of 11, I have 1 times 10 to the negative 11 molar hydroxide ions, which is a much smaller amount than my hydrogen ions, which makes sense. More hydrogen ions than hydroxide ions, so this must be an acidic solution. Continuing on, 1 times 10 to the negative 7 molar neutral, 1 times 10 to the negative third molar for my basic at a pOH of 3 or a pH of 11, and then here 1 times 10 to the negative 0 molar at the end. We can do calculations with pH and pOH, and to do that we use our pH square. You also have these calculations in your packets. And they are on the page underneath equilibrium. So you'll see them here. We have all of our pH calculations. So pH negative log of H plus, pOH negative log of OH, pH plus pOH equals 14. And then we will also use this one, hydrogen ions plus or times hydroxide ions is 1 times 10 to the negative 14. So we can set those up in a square, which helps us kind of organize where we are and where we're going. So if I have my pH and my pOH at the top, hydrogen ion concentration and hydroxide ion concentration, to get from pH to pOH, pH plus pOH equals 14. And to get from hydrogen ion concentration to hydroxide, these multiplied together equals 1 times 10 to the negative 14, which has a special name that we'll look at later on in our unit. Going from pH to hydrogen ion concentration, my pH is equal to the negative log of my hydrogen ion concentration, and hydrogen ion concentration is 10 to the negative pH. And these buttons are opposite of each other on your calculator. So we can see here we've got our log button, and then we've got our 10 to the x right above it, so it's pretty convenient for us. So let's do an example. If we calculate the hydroxide ion concentration with a pH of 4, so I'm starting here at pH, and I want to get to hydroxide ion concentration, so I'm going to do 2 steps to get there. I like to avoid this step if at all possible, just because there's so many things to punch in my calculator and places to go wrong. So I like to go on top and then to the side, because I'm just doing addition and subtraction at the top, which is an easier thing to do usually in my head, but easy to plug into the calculator too. So given my pH of 4, I'm going to first calculate my pOH, and my pOH is equal to 14 minus my pH, so 14 minus 4 is 10. And then my hydroxide ion concentration, if I have a whole number, pH and pOH, just 1 times 10 to the negative pOH, so 1 times 10 to the negative 10, and it's a concentration, so I'm going to have molarity for my units. In my next one, I don't have a whole number or a base of 1, so I'm going to have to actually plug things into my calculator. So if we're given our hydrogen ion concentration of 2.5 times 10 to the negative 3 molar, we're starting here on our square, and we're asked to go to the opposite corner of pOH. So again, I'm going to come up and across as opposed to going through this equation here. So first I'm going to find my pH, and pH is equal to the negative log of my hydrogen ion concentration. So the negative log of my hydrogen ion concentration, which is 2.5 times 10 to the negative 3, gives me 2.6 as my pH. And pH does not have units. So now I can go across to get to pOH. So my pOH, again, is 14 minus my pH. So 14 minus 2.6 is 11.4. 14 minus 2.6, 11.4. And that would be our answer. We can also look at solutions of strong acids and bases and weak acids and bases and determine their pH. If I have a strong acid and base, I can just use the stoichiometric ratio because it's fully dissociated. So I know however much my concentration is of my solid, that is going to be the same as my concentration of my ions if they're in a 1-to-1 ratio. Otherwise, I'll use stoichiometry to figure out what their ratio is. Weak acids and bases do not fully dissolve in our solutions. They don't fully dissociate. So just like before in our equilibrium unit, we used KEQ values or KSP values for our insoluble salts. We're going to have to do that again, except we're going to have Ka values and Kb values for acids and for bases. So let's do one more example. I want to calculate the pH when 2 grams of potassium hydroxide is dissolved in 250 milliliters of water. Potassium hydroxide is a strong base. So first I need to figure out what is my concentration of my hydroxide ions in strong bases. We know fully dissolve into hydroxide ions. We just need to know what ratio they dissolve into. So I'm going to first convert from my grams to moles. So 2 grams of KOH. The molar mass of potassium hydroxide is 56.11 grams per 1 mole of KOH. So I get 0.0356 moles of KOH. So if I have 0.0356 moles of KOH, I know that for every 1 mole of potassium hydroxide, I have 1 mole of hydroxide ions, right? There's 1 hydroxide ion for every 1 potassium hydroxide. That means that I have 0.0356 moles of hydroxide ions also floating around in solution because it fully dissociated. So all of my potassium hydroxide, we could write as an equation, solid fully dissociates into potassium ions that are aqueous and hydroxide ions that are aqueous. Okay, completely goes, which is why I can use this one-sided arrow. Now we want to figure out its concentration. So we have to divide by our volume, 0.250 liters. And I get a concentration of 0.142 molar for my hydroxide ions. Okay. If I have hydroxide ions and I want to calculate pH, I'm going to first figure out my POH, because my POH is the negative log of my hydroxide ion concentration. It's the negative log of 0.142. Plugging that in my calculator, negative log 142 is 0.848. And that is a POH, so no units on that. And then my pH, which is what I've been asked to find, again is 14 minus my POH. So 14 minus 0.848. And I get 13.15. Looking at sig figs here, I've got 3 sig figs and 2 sig figs, so this is going to round to just 13. So my pH equals 13. And we'll practice more of that in class tomorrow.